So just wanted to quickly review the big ideas from the probability stuff so far. And keeping in mind, remember, probability is number of ways that we can, whatever we're interested in, number of ways that can happen out of the total possible ways. And so as we do these, we'll kind of talk through relating it back to that formula. Okay, and then we had the two, and I want to write this down somewhere, but just for a quick discussion. The two big questions that you start off with, or the first big question I should say, is it or is it and? And then if it's or, we have to ask about if it's mutually exclusive, and if it's and, we have to ask about is it independent. So why? Like, what does, first of all, what is the big difference between or probability versus and probability? Yeah.
Or probability increases, the probability increases and probability decreases.
Okay, good. So or typically increases and decreases. There's also an operational difference. So if you look at the or, both of them are addition. I mean, we have to subtract off this little overlapping double count part for the non-mutually exclusive, but they're both addition, whereas and probability is multiplication. And that supports what you said about the probability increasing for or and decreasing for and. Okay? So big question, is it or is it and? That's what you should ask first. Now, this section, it was all and probability because we were practicing with the independent stuff. But do get in the habit of asking that. And one thing I want to address that came up on Friday that I did mention was going to happen, and so it's really important that you get this figured out. Let's just look on page 5 for now. About 25% of Americans put ketchup directly on their fries rather than on the plate.
It's so much better than
Only the weird ones do that.
Oh, but it looks prettier and it's more even, so I don't even want to.
Yeah, it all even.
Okay, so just curious, out of this class, are you the only one? Or raise your hand if you do that.
What? Why?
Okay, so 3.
It makes them so red.
And like, if you do it, you can put more in one spot, then you can.
If
you put it on the plate, you're not
they're
going to
dead
get
rough.
the time to fry on it, so it's still going to
Well, obviously
just.
we're talking
Well,
about
there's
fries.
other ways for it. Like, say you do.
Okay.
You don't.
You make
We'll just let you meet. It's fine. It works.
I think either one.
I think
I agree.
I think
Anyway, here's the idea.
You don't put ketchup on your french fries?
Now you go.
Okay.
When you read this problem, it kind of divides it into you do put ketchup on your fries like directly, or you don't put ketchup on your fries. Okay, drop it and let's move on. Don't miss this. This is going to happen, and it already has, so I want to make sure that we don't have this happen anymore. You can think of this as a either or case like this, like a yes or a no. And what happens, especially when we get to the end of this unit, we have this giant probability concept in our head, is this becomes a 50-50 concept for some people. And so is that correct? But do you see how it can happen? Yeah, like people either do or don't, so it must be 50-50. And that's, if you look through all these options, so keep that in mind. Look at the next page. 84% of Americans pour shampoo into their hand rather than on their hair. So again, it could either be a yes or a no kind of question. Yes, they do it. No, they don't. So it's 50-50. And then you run your probability 50-50 and miss that it's actually 84-16. Okay? And again, as we get towards the end of the unit, and there is a lot of stuff. This is a big unit of new concepts. That can happen. So I want you to maybe make a note. In fact, let's just maybe write a caution on here, on your note packet. that just because there are two options doesn't mean it's 50-50. Okay, so I'm gonna hopefully make this stand out. A couple exclamations and a box here, something like that. Be careful with reading it too simple like that. Okay. Let's go ahead and check. We talked through this first one. Remember, it was this is page 4, number 2 is where we started. So 5/36 because it was not and then yes. So no and then yes on the doubles. The probability of not is way bigger. So 5/6 versus 1/6. So you should have got 5/36 on it. And let's see, we scrolled through most of that. C, D, and E in order go 5/36, 1/36, and 25/36. Now I left all mine in fractions, so hopefully you have some work to support your decimal that you can check with mine. If not, say, hey, can you hold on while I convert? And then have fast fingers to do that.
Oh, yeah.
Alright, everybody's good on those? Okay, number 3, you should have got 1/16. 1/16, which is roughly 8%. Good on that? Because you need, no, not 16%.
Yeah, we got that. I don't know what the rest
Guys, if something goes wrong and you don't get it right, please holler. Let's make sure you figure this out.
I got 1 out of 64 because it says what's the probability that both your school principal and your celebrity, and I read that as 2 principals and 1 celebrity.
Oh, okay.
But I would have.
Okay. Alright, next one. Again, I told you you didn't have to do the area models, but take note of what they look like. Alright. Of course, our current president is Biden, not Trump. At least not for now. 70.56% on that one. Any questions on that one? Okay, next one. Is rolling dice independent? Is that a fairly independent practice? Yeah, it is. Okay, the probability you should have got 5 out of 216, or before you reduce 30 out of 1296. Did you guys get that? Okay. All right, next one. Final simplified version is 5 out of 7,776. Or before that, 60 out of 46,656. Are you getting them right? I can't really tell.
It's 60-40 right now.
60-40?
Nah, probably like 7:30.
Right. Number or part B. It's just the multiplication rule. That's all. That's just with the C added. That's all that is. All right, page 7. Okay. You are totally welcome to write HTHTTHH in here. In fact, that's how I would prefer you to do it. Okay? You don't need to write a little and in between each letter because this is describing that situation without having to write that. Anyway, 0.0078 as a percent would be 0.78%. And then, or if you did a fraction, it's just 1 out of 128. You guys basically taking, and I can't write on here, but I think I'll just grab this and put it here. This is important to notice because it might save you a little bit of time. So, H, T, H, T, T, H, H. If we wrote it out long, each one has a half, like 1 out of 2%. Or sorry, 1 out of 2 probability. Like that. But what is that the same as?
0.5 to
Or 1/2 to the 7th power, right?
Oh, really?
Well, what's 1 to the 7th power?
7.
No.
No.
1.
Yeah.
What's 2 to the 7th power? There's your 128.
A number.
Okay?
I knew that.
So think of that like the fact that multiplying something by itself repeatedly is the definition of an exponent, right? Or at least a whole number exponent. So this is just 1/2 to the 7th power. Okay, next one is exactly the same. Does it matter what order we ask about?
Nope.
Nope. Only if the probability changed for each outcome. But with the coin, it doesn't. Okay, part C. So this is the same idea, 0.279 to the 5th, because we asked about 5 different students. So that gives you 0.169%. That should tell you that, what does that tell you?
We get that one wrong. Yeah.
Well, I mean, obviously, just this number, most kids go to city schools, right? Not rural. I don't know what ours, I think ours would be considered a city, not rural. Okay, part D. 0.978 to the 10th. So all 10 students are not homeschooled. That's 80% roughly. The second one, you have to do 5 of each. So 5 homeschooled times 5 not homeschooled. You cannot just cut it off and say 5 homeschooled, because now you're only talking about 5 kids, not 5 of 10. Does that make sense? Okay, so be careful on that one. I put 0 here. The number is not actually 0, but it's really, really close to 0.
Yeah, it's like 0.6 zeros and then.
Yeah. Like if you put it on your calculator, there will be some numbers, but it's just so far to the right that it's essentially 0. All right. So why did I put not independent on E?
I didn't do that, but I was saying when I did it, there's no way that this is independent. Because there's like a good chance that if somebody in your family is doing it, this more going to do it.
Well, because like, not,
You can't do it in probability.
You can't use the multiplication rule if they're not independent.
and it's
You
like,
can still do it. Yeah.
Since they're part of the same family, the chances that one student's homeschooled but not the others are pretty low.
Yeah.
It's like they affect each other.
Yeah. That's true. Like our kids, my wife and I's kids, we homeschooled them till 8th grade. And then for 1 year, one was homeschooled and one was not, and then now they're both not. So he's right. Like it definitely affected the probability, right? It was not independent for us. Anybody else know homeschool kids? This valley has actually a pretty big homeschool population. It probably would definitely not be 2.2%. I guess it's much higher than that. But nationally, I think that's probably where that's from. All right. Number 8. Tree graphs. Did anybody draw the tree graph?
Not for that.
It's not too bad.
I didn't
But I do want you to take note of it. I've shown you this. Now I think this is the 3rd time. So a weighted tree graph, where as you draw each branch, you put the probability on there, and then you just multiply your way out, basically. Because there we go. Are having children independent of each other? Is the gender like independent of the previous kid? That's really what I'm asking. Speaking of, that is not a sound we hear very often here.
I mean, there's a 51% chance that's a boy, so.
Yeah. I couldn't tell just by the voice, but this is why you make good choices in high school, so you don't have that in class, right?
Wow.
I mean, that's.
That's fine.
You can just sit here and learn, and you don't have to deal with your kid. That's
That's
something to keep in mind.
I mean,
All right. Anyway, do you think we can consider these independent?
No.
Like for real? Does the gender of your first kid affect the gender of your next kid?
No.
No. Like that kid doesn't. There might be some biological thing that might, but probably it's independent.
That kid
Right?
can't be like, I want a sister.
So because of that, we can just multiply out, going out each branch. So this one ends up being just under 37%. Questions on the packet? How did it go overall? Do you think, like, give me out of 10. 10. What do you think you got?
4.
Oh.
I mean, the more practice, I'm getting a lot more
7.
confident.
Okay.
It's just a small thing.
All right.
I got.
So just take note of what you're holding up, and this is kind of hard, isn't it? I don't want to say this too much, but it is kind of true. This is probably going to feel like the hardest unit in geometry. So stay on top of it. Stay on top of it. Stay on top of it.
This is probably
Yeah.
All right. Yeah. Whatever you need to do to get ready for the next stuff. What if things are not independent? So we say it with conditions, meaning I already know something about the scenario, so that probably affects the probability. Okay? For example, if I look at the weather and it says 50% chance of rain, let's go 40%. And I say, what's the probability I'll take an umbrella with me to work when it's 40% chance? Well, if I look out the window and it's raining, now I know something, and that has changed the probability. So that is a condition, right? I will take an umbrella, even if the forecast still says 40% chance. So that's an example. Kind of like if I draw 3 cards out of a deck, that condition has now changed the probability for the next person who draws cards out of that deck, because I have 3 of them.
And if you draw 3 of clubs, the next person's not going to draw. Not going to have a possibility to draw 3 of clubs.
Okay. Yeah.
Out of one shared deck. With all 4 suits.
Yeah. Here's another example. If I said, what is the probability that a sophomore has an A in math?
I have B.
Or let's say has a passing grade in math. Let's say that. Passing, and we're gonna not be like like our school and say a D is passing. We're gonna say a C is passing. So overall in the school, That would be, I don't know what the percentage is, I don't know, but that would be some number. But if I said, hey, let's look at this class, that changes the probability. Why?
Because most of us have
It's a smaller amount.
It's not just because it's smaller, but what's true about this class? Like,
It's hard.
this isn't your typical class, right?
Yes.
Like of students. I mean, you guys are up here versus most sophomore and regular students. So typically, and of course we have a big mix of freshmen to juniors, but still, it's a unique mix. It's not your typical class. So if they just said, hey, pick a kid at random, are they passing math? That's a different probability than pick this class, are they passing math? Does that make sense? Because now we've changed the condition. Okay? So we call that conditional probability, and it's kind of interesting too, just like all this stuff was. Did we not get through all of the pages? We did. Oh yeah, I was on the other slide. I was like, wait a minute. Okay, so look at this big question. How are conditional probability and independence related? So hopefully your brain kind of went to independence when I said that. Because if I, again, with this class example, is it independent now if I'm saying we know it's this class we're talking about? It's not really independent because there's a condition that's making it a different scenario. So this is where we're going to address the non-independent issue that we haven't seen yet. All right. So this one's kind of worded weird. Go ahead and read it. I think it helps if you take this out, first of all, but also we'll talk about it after that. Okay, so big question first. Well, let's make sure everybody's clear. This is a fair bit bigger than that, right? So there's more girls at this dance. It says, of all attendees, 20% won a prize. Okay, assuming that the number of senior girls and boys are equal, estimate the probability that a randomly selected senior won a prize. So let's do that one in a second. I want to ask you this one first. If you knew whether the selected student was a boy or girl, would your estimate change? So that's that condition part, right? Does it change the probability if we know the gender of the person who won the prize? How? Or why? Maybe I should say why. Yeah.
Because it would be the total.
Okay, so it's narrowing down the total to one group. Good. And also because more girls went, right? Okay. I think we'll come back to do this one. It's going to take a minute. I just want to introduce this concept a little and show you something that is called a two-way table. Two ways, meaning sideways and up and down. Okay, so I'm going to briefly orient you to this and then we'll start using it tomorrow. So we have totals of two different categories. So obviously the age group and then in this case class type. this bottom right corner is the overall total, and it should be the same going horizontal and vertical, okay? If it's not, there's some issue with your table. So that would be one of the first things I check. So we can start asking things like this. If I just said probability that you pick a senior at random, what would you say? So here's all the seniors,
You have 39.
and we have 115 students. So it's just 39 out of 150. Okay, so that's one direction, two-way frequency table. That's one of them. Then I could say, what's the probability that you chose a drama student? What would that be? 17 out of 115. That's the other direction. So do you see why it's called two-way? And then here's where we get into the real nice thing about these tables, is if I said junior and drama. That's just this one, right? And that is not independent, but it's allowing us to answer non-independent questions with this table. Okay, so the table problems are going to be kind of nice. We won't just do them, but that is a quick orientation, just to shove that in at the end. So we'll pick up there tomorrow.